Hey guys, welcome to Chapter 2, Section 2, Matter and Changes in Matter. We got a lot going on today, a lot of demos with this. We're covering a lot of material. So sit tight, hang on, be ready to hit the pause if you need it for notes, etc., or annotating your outline, but here we go. Matter, first off. Matter is anything that has mass and takes up space, like my beaker here, or a chunk of salt, or a canister, pretty much anything. Now it exists in three states. It can be solid, it can be liquid, but it's also the gas, the air I'm breathing. It's made up of nitrogen, oxygen, carbon monoxide, carbon dioxide. But can be any of these, as long as it takes up space. Gases are a matter because takes up space. There is air in there. I let it out and it blows my hair. So just because we can't see it doesn't mean it's not matter. Now, not everything is matter. Sound isn't matter. It's energy. A thought is not matter. So something can be real but not matter. But as long as it has mass, takes up space, it is. Comes in two chemical forms basically, element or a compound. My aluminum foil here, well, aluminum is an element, but this big chunk of salt, however, is a compound. Different thing, it's made up of two different, sodium chloride. All aluminum, aluminum, sodium chloride, lots of sodium plus the chlorides bonded together. Now, elements all have unique properties. My aluminum, it's shiny, it's malleable, I can flatten it out. Oxygen is clear, odorless, it's a gas, light. They have different properties. Gold tends to have a unique color as opposed to aluminum. Now, most metals tend to be shiny, most non-metals tend to be dull, some common characteristics, but anyway. And elements cannot be broken down into other substances. I can't break this down into anything but aluminum. This I could break down into sodium and chloride, or not that it's water, but if I have water, it could be broken down into hydrogen and oxygen. But oxygen, I can't break it down further into anything else. So difference between them. Now, elements, let's talk about them. I say it can't be broken down into anything else. Let's go through more of a thought exercise, but I can take this and I can tear it in half. I can tear it in half, tear it in half. Each time I tear it in half, I still have tinfoil. It's just getting smaller and smaller. It doesn't take me very many tears before I'm down to a teeny tiny piece of tinfoil. Now, I could tear it again a few more times, but eventually, if I kept tearing this down and then I got it under a microscope and I kept tearing it apart, eventually I would get to something so small I couldn't separate it any more, and that would be an atom of aluminum. So that's a different. Salt, however, is a little different. I take this big chunk of salt and I could grind it. Well, I'm not going to because I don't have to, because I've got salt in here and it's already in smaller crystals. I can take that and then grind it again into even smaller bits. Let me get one a little bigger that I can see. And I can take, one of those. Eventually I'll get down to a molecule with a sodium and a chloride bonded together. Now, I could break that apart and I would have a sodium atom and a chloride atom. So that's kind of your classic difference in an element and a compound. An element is all made up of one type of atom. A compound is made up of two or more. Sodium chloride. In this case, it's actually sodium hydroxide. Sodium OA, hydrogen and oxygen, three bonded together. In this case, we have some sulfuric acid, H2SO4. It's a compound where they're bonded in together. So elements, all one type of atom. Compound, two or more bonded together at the molecular level. Now, each element has its own unique atomic number. So I'm going to throw a periodic table element back here. Let's just look at carbon, very classic one that we look at. Now, typically, within the proton, we're going to have the same number of protons in it. So its atomic number. So up here, if you notice it says 6, might be hard to see, but look at a periodic table. Its atomic number is 6. That means it has 6 protons in the nucleus. And then the mass number is the number of protons and neutrons in the nucleus. So you notice here, its atomic number is 12, meaning it has 6 protons, 6 neutrons. Now the number of neutrons are not always exactly the same as the protons, and that's where we get to different isotopes. Oh, I'm going to throw up here now carbon 14. It still has 6 protons. 6 protons is what makes it carbon. If it had 5 protons, it would be boron. If it had 7 protons, it would be nitrogen. If it had 8 protons, it would be oxygen. The number of protons dictate the element. The number of neutrons added to the number of protons makes up the atomic or the mass number. Atomic mass number, sometimes just known as mass number, how heavy it is. And then if it has, so carbon 14 is an isotope of carbon 12. Carbon 12 is what most of the carbon in your body or in a tree is made up of, but a small percentage of carbon in your body will be carbon 14. It is an isotope. It is radioactive. It's unstable. It doesn't like being carbon 14. It's more stable at carbon 12, and eventually the nucleus breaks off and sends off an alpha particle, beta particle, a little bit of radiation leaks out in a known amount of time. So every element has a unique atomic number, the number of protons in it. It will have a mass number, 12 or possibly 14 in the case of carbon. Carbon 12 is the usual one, and carbon 14 would be an isotope. And this takes us to atomic theory. All elements are made of atoms. This is the basic theory that comes through. Lots of experiments in the past, lots of people contributing to this theory. A why, what are things made up of? Why is it here? It's the individual atom, and each atom is made up of 3 subatomic particles. Now we're not going to go into quantum theory from here. We're going to leave it at the subatomic particles. Protons, which we already talked about, protons have a positive charge. Neutrons have a neutral charge, so P for positive, nu for neutral. And then electrons, which orbit on the outside, are negative. Electron, neg. I kind of focus on that E part. Remember, it's negative. Protons are positive, neutrons are neutral, electrons are negative. Protons and neutrons in the nucleus, electrons swarming on the outside. So, the atomic number, as we mentioned, is always going to be equal to the number of protons. So you look in there and you find nitrogen, and lo and behold, its atomic number is 7, has 7 protons in it. You look up oxygen, and lo and behold, you find out it has 8 is its atomic number. It has 8 protons. You find iron, pretty sure that it's 26, number of protons in it. You go all the way up to uranium, 92. That's the number of protons in the nucleus. So then the mass number is going to be the total number of protons and neutrons. So when you look through, they're not always equal number of protons to neutrons, but the mass number we look at and determine. So in carbon 12, 6 and 6. Carbon 14, 6 protons. Has to have 6 protons or it's not carbon, but in this case it has 8 neutrons, giving an atomic number of 14, the number of protons and neutrons. The electrons are 2,000 times smaller than a proton or a neutron, and they really just do not contribute to its mass. So the protons and neutrons equal the mass. Now we've mentioned carbon-14. It's an isotope. It's the same element, still carbon, but it has a different mass number. Carbon-14 as opposed to carbon-12. This makes it an isotope. Now molecules, we talked about like my compound of salt. Well, if I get down to an individual molecule, it would be one atom of sodium, one atom of chloride, or whatever. But a molecule is going to be a combination of two or more atoms. Oxygen forms in a molecule, O2, and it's going to be same or different. So this molecule of salt would be sodium chloride. A molecule of oxygen, which I'm breathing, would be O2. And they're held together by chemical bonds. Chemical bonds is where we talk about ions. Those electrons around the outside, well, things want certain number of electrons on their outer shell. The first shell can have 2 electrons, the next shell out can have 8. Well, if something only has 6, like oxygen, atomic number of 8, 2 electrons on the inner shell, only 6 on the outer, it kind of wants 2 more. So it tends to bond with something else. And this is where we get ions. Those electrons can be either shared or given off. So let's look at a Simple demo of an ion using a balloon here. All right. Trying to get it big enough for this to work well, but not so big it'll pop and scare me half to death. So, now my balloon. If I rub on my hair, now I probably should not have used conditioner in my hair this morning, but it'll probably still work. Now what I am doing is I am literally scrubbing off, yeah, I know, I'm messing my hair up. I am literally scrubbing off electrons from my head, and they're being attracted to the balloon as I take it down near the surface of my, can't get things in the way. They usually attract. Let me see if it's working with my pepper. Well, I'm not getting very good static electricity. It's pretty warm, kind of humid here today. But anyway, the balloon we've seen before, you can stick it on something that makes your hair stick up. The balloon, I'm stripping electrons onto here, so making it negatively charged, leaving my head slightly positively charged. So this winds up being charged. It's an ion for a while. It just forms when electrons are gained or lost. So I could have a negative ion or a positive ion, either way. All right, well, that one didn't go too great. Well, let's look at another, acidity. Now things with acid in it. This one also looks funny because my solution here is green, so often with my screen it kind of may look funny, but let's take a look. Now acids come with a pH. Neutral is green. Now this is a universal indicator. It lets us know if something is acidic or basic. Now this is sulfuric acid, H2SO4. Now acids tend to turn pink in a solution, and sure enough, my vial goes nice and pink. I'll leave this one in the middle as a indicator, and over here I have sodium hydroxide, which is a strong base, and if I put some of that in, it goes from a blue to a purple. So I have a strong base, neutral, and a strong acid. pH below 7 is an acid. In this case, it's a very strong one, around 1. pH of 14, my sodium hydroxide, is that, and 7, pure neutral. Pure H2O would be neutral, but a neutral solution. So a little bit about, and we'll run some tests, get some practice with it, etc. Chemical formulas. So NaCl, sodium chloride, H2O, water. These are chemical formulas. H2SO4 for my acid, NaOH, sodium hydroxide. This is our chemical formula letting us know what something is, what type of atom or ion is in there. Then we have ionic compounds and covalent. Well, ion remembers to the electron. Things can share, give away electron or take an electron. So ionic compounds are compounds where one gives away an electron to the other. So it makes them bond together. A covalent is where they both share an electron. So ionic, one is either giving away or taking from the other. And in the covalent bond, they are sharing with each other. This takes us to organic compounds. And I'm going to run through this pretty quick here because we'll have some opportunity to talk about it later. Organic compounds and organic chemistry, it's things with at least 2 carbon atoms in it, with the exception of methane. Methane is CH4. Methane is kind of classic where we get flame from, but we'll burn it as a gas. It is an organic compound, but most things have at least 2 in it. You are a carbon-based life form. You're made of hydrocarbons, and this is where organic compounds come from. We either have hydrocarbons like you or a tree, most living things, or simple carbohydrates like sugars for the most part. Now, macromolecules, these are complex organic molecules, such as proteins, like what makes up muscles, etc. The nucleic acids, like DNA, deoxyribonucleic acid, or just ribonucleic acid, and the RNAs, and lipids, or fats. These are what we call macromolecules, very large interconnected molecules with lots of different, not just 1 or 2. Sodium chloride, very simple. Where you get into sugars and other things, and there are these long, complex chains of carbons, hydrogens, and other elements bonded in together. Which kind of takes us into these cells, genes, and chromosomes. Now, you should have learned about this when you studied life science to a degree, possibly biology, depending on where you're at in your studies. But let's look at it in a certain fashion. In your body, you are made up of cells. In a single cell, there will be a nucleus. Inside of the nucleus, we will find chromosomes. Chromosomes are made up of a long strand of DNA, and on that strand of DNA will be individual genes. So we want to make sure we get it. So if I start at the very bottom, I have a gene, which is just a small section of a DNA strand. The entire DNA strand, all coiled and woven together, will make up a chromosome. You will have 23 pair of chromosomes inside of your nucleus, and the nucleus is inside of a greater cell, whether it's a skin cell, hair cell, muscle cell, etc. A collection of cells make up tissue like skin. Makes tissue. A collection of tissues make an organ. A collection of organs makes an organ system, and a collection of organ systems makes an organism. So we kind of want to make sure we still recall this basic breakdown. So once again, chromosomes are composed of many different genes. A chromosome is one long strand of DNA that's just been wound up and organized. So one chromosome will have multiple genes on it, which are individual pieces of our DNA strand. And the picture we have up here that we're having with it is just sort of a breakdown of a DNA sequence showing the little different pairs on it that we won't break down too much more, but just understanding that a chromosome is made up of DNA. Genes are located on the individual strands of the DNA, which is chromosome. Chromosomes are found within the nucleus of a cell, and the nucleus is inside of our cell. Cells together make up a tissue. A collection of tissues makes up an organ. A collection of organ systems makes up an organism. So, taking us to physical and chemical changes. Now, physical change. I have a piece of paper here. Now I can change its size, in a sense, by folding it in half. I can make it smaller, a rectangle. I can turn it into a triangle. I could crumple it into a ball. These are physical changes, but it's still paper. I can tear it in half. It's a smaller piece of paper, kind of like we did with the tin foil. You know, I can take tin foil, once again, flat, and turn it into a ball. I can rip it in half, but it's still aluminum. I haven't changed fundamentally what it is. A chemical change, however, is a little different. I take my same tea bag. It has the chemical property of that it will burn. So I light it, and it's no longer paper. It's ash. It's probably floating back down the area. So it's ash now. No longer paper. It's just its carbon components. Some of that hydrocarbon has been released in the form of carbon dioxide and some water vapor. And what I have left over is just basically carbon. It's not paper anymore. A chemical change. Now, there are different signs of a chemical change. Let me rearrange some of this. In here, I have potassium permanganate. Really dark. It's actually a purple color. I try not to get in my hands because it stains really bad. And I have pure glycerin, like what you might find in nitroglycerin. Glycerin itself is fairly harmless, but if I put the two together, I tend to get a chemical change. Now, a chemical change is evidenced by several things, or at least we have signs. You can see here I have bubbling, I have smoke being given off. That smoke is a sign of a gas being created, and the gas being created is showing, and ta-da, energy being given off. These are all signs of a chemical change. I'm just going to cover it up so I can cut the oxygen off and blow it out. You can also notice another thing in here. You see the water vapor forming around it. It tends to cause it. A chemical change. Change in color, a change in odor, a change in energy, gave off heat, and scent. These are some of the signs of a chemical change. When there's a chemical change, then I have a different substance. I no longer have potassium permanganate and glycerin. I was giving off a lot of heat, give some carbon monoxide, carbon dioxide off, some water vapor. We can see where the water vapor has formed around. There's my carbon dioxide escaping away. I'll blow it out. Our water vapor has formed around. I have different products than what I started with, defining a chemical change. And that leaves us with the law of conservation of matter. We can change elements and compounds from one physical form or a chemical form to another. So I changed my potassium permanganate into some carbon monoxide, carbon dioxide, water vapor, and I'm left with some carbon down in the bottom as well. I could change my paper from paper into ash or carbon, but I can't destroy the atoms. The atoms are still here, they've just been rearranged. If I were to separate my sodium from my chloride, I would still have sodium and chloride. I just wouldn't have salt. If I take water and I break it apart into hydrogen and oxygen, I still have 2 atoms of oxygen for every 2 atoms of hydrogen for every 1 atom of oxygen. I can't destroy matter. I can only transform it by one form into another. Well, that's it, guys. That wraps it up for section 2. Take care, and we'll see you next time.